Good afternoon, all the participants, and thank you for participating at the fourth episode of the ETN CCUS webinar series. Today, we invited Jeroen Michiels from Everllence, former Manager Solutions. We actually found out yesterday that the company changed its name quite recently. Jeroen is a sales manager for CCS and CCUS at Everllence, and he will provide us today an overview of the CO₂ solutions for the compressors developed by his company. So we would stop here our introduction. I would like to thank Jeroen for your availability to attend today's webinar. So please, the floor is yours. Thank you.
Thank you very much. Thank you for having me and for the nice introduction. I hope I can get everything in time. Should just fit. If you have any questions, don't hesitate. So a little bit about the company. Like Nicolas said, we changed the name from Manager Solutions to Everllence. It's building a new brand for a company without the man, truck and bus idea behind it as well. So the company is a part of the Volkswagen Group. As you can see here, the passenger cars, the commercial vehicles, also known as truck and bus, and now Everllence for the engineering part. We're the smallest part of the entire group, but they see us as the engineering group, the engineering part of the organization. We have roughly 50,000 people working on us, present in over 50 countries, 140 sites all around the world, exist over 260 years already. Started somewhere in Oberhausen in the St. Anthony's, and from there it grew, integrated several companies, parts of Schulze, Borzig, you name it. And for now, it's also a good step to make a new name with all brands on the one name. These are the production locations, mainly in Europe, a few in India, one in China. We have service locations all over the world. Because we also have a marine side to our business, there are also a lot of service locations based on coastal areas. Started in 1758 at St. Anthony's, like I already said. Headquarters founded in Augsburg. That was founded in 1840. Yeah, so this is how it all began with Mr. Diesel in the middle of that. Our strategic direction, moving big things to zero. We are aiming to work on the decarbonization globally, and we do that with our equipment. So part of it is power to X. We're producing reactors to make methanol or SAF or other synthetic fuels. Future fuel engines for the marine side. We're developing ammonia engines right now, retrofits on ship engines, so it can dual fuel, so they can run on partly on methanol, the carbon capture, of course, and large-scale heat pumps up to 100 megawatt thermal. We'd like to try to, our goal is at least to decarbonize globally by 10% by the use of these equipments. So from the marine side, CCS, heat pumps, but also the electrolyzers we produce within our sister company, Quest One. Then I come to the carbon capture part. If we're looking at CCS, we'll first of all have to look at where is CO2 hard to abate. It's the known players, I think, the cement industry, the chemicals, refineries, but also the power industry. Then you have to capture your CO2. There are several types of capturing systems on the market. This is a amine-based system based on absorption, where the CO2 is linked to amine then freed and returned to the amine column. And the CO2 is then processed further to the compressor. That is where we come in. We provide compressors. This is an example of a CO2 compressor, 7-stage machine. First 5 stages are for wet CO2 in this case, and the last 2 for dry CO2. Then if you have a compromise, then you have to think, what do you want to do with it? Do you want to have ship transport, or do you want truck transport or pipeline? It all differs in what way you want to compress your CO2. So there are a lot of options for the use of CO2. The main focus right now is sequestration, where you can, for instance, do what they do at Porthos and sequestrate it offshore and depleted gas fields, or onshore, which is a little bit harder to realize in the western part of Europe. Then we also can create, for instance, a liquid lake of CO2, not that popular, where the water pressure and temperature will keep it down, and dilution, not very popular, especially then with environmental groups. Also have to look at the utilization part. So CO2 we can use in combination, for instance, with hydrogen with power to X, but also you can use it in the fertilizer industry of mineralization. There are several options for that. Only the majority of the solutions is right now sequestration. Then if you want to transport it, you can make it a gaseous form for short-term transport, similar at what happens at Porthos. Liquefaction for ship transport, for instance, Northern Lights, or supercritical for long-distance pipelines. Then we have to take a look at the technology readiness level. The capturing part, like I said, there are varieties of capturing systems. So absorption, membrane systems, cryogenic systems. Yeah, there are a lot of new solutions coming to the market. Solutions that are made better over the years. But again, it depends on how much CO2, what is the purity of the CO2 you need. And that's an important part to look at. If you then take a look at transport, pipeline, shipping, but also trucks and rail, but that makes it very expensive, or more expensive for the transport. Utilization part, there are a lot of utilization possibilities. Some are ready for market, some are still in development. And then the storage, EOR, enhanced oil recovery, is one of them, where you repressurize the oil field to take out the remaining oil, or leave it in depleted gas fields, for instance. So this is what happens in Europe at the moment in last years up to 2023. A lot of projects have been developed, are under development, are being built as we speak. The Northern Lights project, that means Brevik, the cement factory, is up and running. Porthos will be ready at the beginning of next year. Then average cost. This is an example of a calculation where a coal power plant has got a CCS project. Then first you have to have the capturing system, so the cost in US dollars, and the share in percentage. Then the transport and compression part, and these 3 together are the most expensive part of such a project. Then you have your injection, monitoring, and the total sum. Of course, it depends on what kind of company or installation you're having, and where you need the carbon capture at. Then we have to take a look at what type of compressor we use for this type of compression. So we take a look at the multi-shaft centrifugal compressor, internally geared centrifugal compressor, which has a mass suction rate up to 500,000. up to 250 bar. This is how such an installation can look like. First, we have here the driver. The coolers are all system, of course, all the piping, and the core unit, the compressor here in the center. We make use of an internal gear change vehicle compressor. In principle, it's a gearbox with the bull gear driving the pinions here, where the gas is injected into the volutes and then compressed. After compression, after each stage, there's an intercooler, and then it returns back to the other side, to the next stage, and so on, so on. We can do this up to 10 stages, but in principle, 10 would be enough, or 8 would be enough. This compressor is nothing new. We've been using it over many, many years for also CO2, also hydrogen, nitric acid, ammonia, you name it. It's a very versatile and a very steady machine with a high availability. Can use it again for liquefaction, gases, and supercritical. We can have heat recovery on this machine, less power, less OPEX. Therefore, it's a really interesting machine. It has a low footprint on the entire installation. And you have to take a look at the CO2 itself. CO2 is a very heavy molecule. Therefore, it's very easy to compress in big stages. And in this case, it regards to in-depth sequestration for compression for sequestration. Every step has an impeller, and the impeller size shrinks, of course, to a very low point where the smallest one is almost the size of a matchbox, where it runs at 40,000 RPM up to 200 bar. The big advantage of this type of impellers, it's mounted on the front of the pinion, and therefore, if you compare it to a regular compressor impeller where it's strung onto the rotor itself, you have a much bigger surface area, and therefore can compress more and faster than a regular impeller size. This is how such a compression can look like. So we start here at atmospheric pressure. First step, cooling, next step, and then up to, in this case, supercritical. If you then want to transport your CO2 by shipping, you have to liquefy it. We use the Joule-Thomson effect, and then you liquefy it to roughly 15 bar minus 28. You can pump it then up to a ship and transport it to your designated location. If you compare it to an gear to an inline compressor that we also provide, this is the reason why we choose for integrated centrifugal compressor for CO2, because it needs less steps. So in 8 steps we can go up to, in this case, 160 bar, where with an inline compressor you will need 15 steps. 1 machine to 2 machines, 1 engine, 2 gearboxes, and all this has an effect on your capex and opex. So if you look at the comparison again, the intergeared has a lower head, uses less power, and is more efficient. It needs less parts. As you can see here in the red, the amount of impellers you need, gearboxes, and so on, and a lot less people to work on it on your overhauls. So that makes it, especially for OPEX, really attractive. We can do also heat recovery between stages, temperatures up to 120, perhaps in some cases already higher. You can produce steam or hot water. You can also have your organic Rankine cycle for energy recovery. So it's a very versatile machine. We also provide modularization systems where you have to find standard casings, shafts, bearings, you name it. Also the piping, framework, instrumentation. That means faster lead time, price reduction, and a faster erection on site. We have, like I said, we have been doing this all over the world for many years. This is an example of our first modularized system in the US. It's a 2 times 40 megawatt machine, compresses up to 167 bars. In Canada, this at Shell, this is where we got our availability for this machine, 98.7%. So we're very happy with that. This is an example of enhanced oil recovery. You can see here that the CO2 is injected in the oil field, and it's then taken out. The oil is then taken out. As you see here, the pipeline, 420 kilometers throughout an oil field in North Dakota. This is our biggest project up to now. These are our 3 biggest machines, the RG90. That means that the impeller, the first stage impeller diameter is 19 centimeters, and it has 8 stages. Here it's used also for getting the natural gas out by repressurizing it with CO2. This is a Northern Lights project, the cement factory, where we provided a compressor system. Here we liquefy the CO2 for ship transport. From there it goes to Ooigaarden. There's a compression station where it's then injected in the old gas fields. We have the cooperation here with Aker Carbon Capture, where we have heat recovery up to 33% back into the capturing system to make it more efficient. And this is how that installation looks like. As you can see here, a couple of guys, MEM truck. Here on top you have the machine, all the piping. And with this type of industry, there's a lot of extra water in the system we have to take out. Therefore, there are some additional equipment. Therefore, it was a little bit bigger than the standard CCS compressor. This is the Porthos project being developed in the Netherlands. We provide here the compressors. There's 3 compressors in total, 3 times in 28.6. It can handle the flow up to 250,000 kilogram per hour. And there, the sequestration amount annually is going to be 2.5 MTPA. And in this video, you see a little bit how that goes. It's from location down into the ocean to the central point. From there, injected in the old gas fields. Next to this one is going to be most likely being announced next year. The sister project Artemis is going to be a copy paste. There's also going to be a liquid storage facility called CO₂ Next. And from here out, they're going to work towards a infrastructure for CO2, where companies can then transport their CO2 towards Porthos or Aramis to have their CO2 sequestrated. It's going to be run towards Germany and perhaps connected there to a similar grid itself. So that was it in short. Still in time? Think so. Are there any questions?
Thank you, Jeroen, for the detailed presentation on the both technical part and also the economics. Before opening, I also found interesting the connections you just reported with the Northern Lights project in Norway with Equinor, which is a project that ETN has visited during its AGM with the members in March this year. So I think it's good that we have this dissemination. And with this in mind, I would like to open the floor for any questions you may have to Jeroen. Also, any comments you may have.
Are there any projects that you are working on when it comes to CCS? Any obstacles you have encountered?
Well, actually, I would have a question to you, Jeroen, because you are involved in the business of this technology, and we often hear how difficult it is to let's say, develop, but also bring to the implementation status these CCS projects, right? So how would you see the business models for CCUS nowadays in Europe? Which difficulties you foresee for the deployment of your technology in the European market?
The main problems are, of course, the financing part, but a very, very important one is the infrastructure. And that's where you see a lot of businesses in Europe struggle to get rid of the CO₂. They are willing to work on CCS. They are willing to look into to capture it, but the main problem is, and then what? And that's where the transport organizations in Europe have a very important role. In the Netherlands, Gasunie, Belgium, Fluxys, or OG, GRT, you name it. You see that in the Netherlands and in Norway, the government and the transport organizations together take a lead in that. As you can see at Northern Lights project, of course, Equinor you named, looking at the development of the CO₂ highway. And then in the Netherlands, you would have the Delta Rhine corridor, Delta Schelde corridor. Those are very important points for development. And hopefully, we will get some more clarity in the beginning of next year in regards to those projects. I see that governments have freed monies for that. You see also in the UK, it starts going now at track 2. In Teesside, that's most likely going to have a positive result for UK and then kickstart other projects for that.
It is promising what is happening, at least in the UK, with this track 2. We also received, when you were talking, a message from Jacqueline. So the compressors for the Northern Lights project is that to repressurize CO₂ for injection after delivery by ship. And does it gather CO₂ from multiple sources?
Breivik, no. Breivik is for Heidelberg itself, meaning that the CO₂ captured there, we liquefy, then transport by ship to Ooigarden. There is a storage facility that's going to be expanded upon the upcoming years. That is the location where the ships will transport their CO₂, liquefied CO₂ to. And from there, it will be repressurized. You need very high pressures for the deep gas fields. For instance, Porto's project is 180 bar at 3,000 meters deep. And you need that high pressure to keep it down.
Then we have Richard. So he's more touching upon the economics. What transport? Oh, wait. I have to retake it. What transport and storage method, pipeline versus road or ship, were you referring in the comparison slide? Or was it a sort of an average?
Which comment are we at?
Pardon?
Which comment are we at? It's the second one from Richard.
Yes, from Richard Hamilton. And if I take your slides, yeah, please.
No, it's the cost for the transport of CO₂ by pipeline is the most efficient and cheap way to do that. I recently spoke to a cement factory in Germany, somewhere down south, and if they had transported by train, because that was the only option, they would have a train there every 10 minutes. And that's just not feasible. There has to be another solution. So then it would be ship transport or pipeline, and that needs to be developed. And if you look at the market projections for the upcoming years, so 2030 to 2050, you see a lot of pipeline developments throughout Europe. And that's somewhere where we are a little bit behind if you look at the US, where there are already a lot of CO2 pipelines available. So that's one of the biggest challenges here in Europe. I hope this answered your question. What's the power consumption of these units? I worked on a project in UK for CCS for generation plants about 16 years ago. Oh, and the power consumption were approximately. Again, that depends on what type of compression you need. And that's something I would like to, if you want to go in detail, to set up a meeting with our engineering department to take a look at what is the situation, what are we looking at? Are we looking at a chemical plant? Are we looking at ship transport, pipeline transport? Are we looking at, there are many variables that have influence on the power. In the case
we have Antoine, indeed, who is so in the case of the CO2 emitting process, which is a fluctuating flue gas prior to capture, is the CO2 compressor capable of supporting a fluctuating CO2 mass flow at the outlet of the capture? And if so, what is the amplitude of the variation it can tolerate?
Again, that is one for engineering department. And I'm happy to set up a meeting.
And then we have another question from Manfred Klein. So on the detailed process methods graph slide for SU2 and liquid pipeline transport. So Manfred is asking whether you could explain that again. So in particular, the differences between the first two examples.
This one, I guess. Liquid pipeline transports. Okay.
Yes. Yes.
Okay. This one, the first one, compressing to supercritical. This is mainly for longer distance pipeline transport. The green line is then for liquefaction. Using the Joule-Thomson effect, liquefying the CO2. From there, you can then pump it onto a ship. For the example at the Northern Lights project. If it's in vapor phase, you can also use it for transport, but then shorter distances. You can also liquefy it halfway, but then it takes more energy to get it liquefied. So this makes less sense. It's more interesting to first make it supercritical and then liquefy it. Does that make sense? Does this answer your question?
Yes, I think your response was comprehensive. Thank you, Jeroen. So we still have time for any questions you may have, either on technical and non-technical topics. Also, if you want to share your own experience or relevant topics.
But might be of interest to show as we have time. Take a look at. There's a small map. This is a map of how the transportation lines roughly going to be up to the next years. that's going to be developed. So what you see here in the Netherlands is the Delta Rhine corridor, then a German transport line. I read that Germany is really progressing now. France is not moving that fast. Let's say have a different approach to CCS. First looking at the industry change, that you have done everything to change your that you have done everything to abate the production of CO2 within your production itself before looking at CCS projects in a different way. There's CO2 highway coming from Norway to Belgium to France to Zeebrugge and to Dunkirk. So these are a few of the things that that we look at, that we keep a track on, and that makes it also interesting for their customers. And of course, it's important to look at what projects are going to develop that have influence on the progress of these projects for A, for the funding, and B, for the infrastructure.
Well, I would say it is astonishing to see this difference between the geographical areas, South and Northern of Europe, considering the potential it may have. So, as an Italian citizen, it was bizarre to see how the pipeline, as it looks now, would be somehow detached from the rest of the continental countries. Exactly.
Yeah. And then if you could zoom in on this map, then it needs more of that, more infrastructure. And then if you look at the eastern part of Europe, there's more companies are looking at on-site of local storage, onshore storage. Because if you, for example, look at Hungary, for instance, they have no sea borders. Where did they go with it? You have to go cross-border. So you have to make agreements with other countries. And for instance, Romania is at the early stage of making rules and regulation within their country on the transportation and capturing of CO2. So that makes it, for them, again, an obstacle. Poland, for instance, is already looking at development, but in the northern side, because they have then access to the water. And if you look at all the possible storage facilities, there is a lot to be had. But again, rules and regulation, environmental questions being raised, political issues playing a part in this. It's an interesting one. And it is something that is developing the upcoming years. Important one is the Portos project getting connection to Germany. And from there, you can, again, work further outwards.
Thank you for sharing this, Jeroen. That gives, from our perspective, more information in comparison to what we had as of now within ETN. So we're actually thinking about in our working group, we're thinking about developing a report on the optimal transportation methods for CO2 for CCS GTs. Is there anybody in the audience who would like to ask a question on this content? So I do not see any comments or questions. Oh yes, there is a question from Manfred. which are the solutions for low carbon percentage GTs?
You mean where there's a low production of CO2? Is that what you mean? Okay. Yes. If you look at the compression systems itself, we mentioned Northern Lights several times. That is a amine-based system from SLB Capturi, formerly known as Aker Carbon Capture. It's a big installation. There are several options for smaller installations, for instance, membrane systems, where it's a different type of capturing, using again, of course, the membranes to capture the CO2 out of your exhaust. If you would like to know more about it, I can put you in contact with producers of said capturing systems. Mostly these are made for lower amounts. What is interesting in the utilization part, if you I've been talking, of course, about big volumes in the cement industry and so on. If you have lower emissions, there is the utilization part that can be very interesting. If you have, for instance, CO2 and you have, for instance, hydrogen, with a reactor, you can create methanol and create a new market for yourself. There's an enormous demand for methanol, especially from the ship industry. I've heard that Maersk is starting to build a factory in Belgium to create methanol from waste plastics, just to supply their own fleet. There are several options.
Fred has also another question. So will gas turbine use exhaust gas recirculation for increasing 4% to 8%?
Sorry, I don't get that question. Okay, so use that I wouldn't know.
We also have a question from Richard. Please, Richard, floor is yours. You can unmute yourself.
Thank you. Hi. I hope you can hear me all right. So I just actually, it's an interesting question that Manfred is asking there. Firstly, EGR, I presume he means exhaust gas recirculation. So this is a method that can be used. It depends on the overall system. So sorry, I should just say, Richard Hamilton from Mitsubishi Heavy Industries. So we do have our proprietary carbon capture method, which is an amine-based solvent. And I was going to point you, if it's not too much of a plug, to the project at Ravenna, Casal Borsetti, which for the last couple of months has been running, capturing the exhaust gas from a small gas turbine, so at about 3%, and we've achieved about 96% capture rate on that. Again, once it's captured and released, then it goes into a suitable compression system, depending on whether you're going into pipeline liquefaction. So yeah, and then you need, in terms of the EGR piece, you need to look at the overall efficiency of the system as to which works better for you. Sometimes it's better to just optimize the carbon capture process, and sometimes you do get a defined benefit from implementing the slight additional cost on exhaust gas recirculation. I hope that answers the question. Apologies for jumping in.
No, Richard, thank you very much. It's very helpful. And especially you as also a provider of the capturing systems can give also another perspective on that part.
Do we have any final remarks or questions before we close today's workshop? I do not see known, so we would like to move to the conclusion of this webinar, which it attracted several attention during the question and answers, which is a good sign. So we are happy to see this active participation from our members. In case you would like to reach Jeroen further for any technical questions you may have, also any information, please let us know. You can contact the ETN office and we can forward the request to Jeroen. And we're happy to help you out in there. So with this in mind, I would like to thanks again, Jeroen, for your availability to present. We'll also make the recording available on our YouTube channel. And we also thank all the participants who joined today's workshop, and we look forward to seeing you online at the next episode in Q3 or Q4 of the year, still to be decided. So thank you very much again, and we wish you a good day ahead.